Okay, today I'm going to look at partial differential equations, PDEs for short, by analytic methods. I say by analytic methods because there are also numerical methods. And we're going to have a glimpse of that in week 12. So introduction to PDEs. A partial differential equation, or PDE, is an equation involving a function and its partial derivatives. The function depends on two or more independent variables. Okay, for example, x, y, and z are spatial dimensions, and you might have a time component. The order of the PDE is the order of the highest derivative, just as it is for ODEs. So the first one we'll look at is the heat equation. The rate at which the temperature changes with respect to time. So that's partial T on partial T, but there's an uppercase and lowercase there. So the rate at which the temperature changes with time is proportional to nabla squared of T, where nabla squared is the sum of the second order partial derivatives with respect to each of the spatial dimensions. So this is an example of the heat equation when you have three spatial dimensions. But of course, you may be looking at a situation in which you only have one or two. Okay, so we could abbreviate this heat equation with subscripts rather than the symbols that look like a backwards 6. Okay, so we could write it as T subscript lowercase t of T, X, Y, and Z. Now, it doesn't have to go in that order, but whatever order you choose, try to be consistent about it. Okay, equals a constant times the sum of the second order partial derivatives with respect to each spatial dimension. All right, now the K depends on the material that the heat is transferring through. So iron, for example, is said to retain heat very well. So that would have a different K value than, say, aluminium. All right, so let's look at some examples of the heat equation and how you might use those. So, for example, if you have a metal rod in which you've got a candle heating up one end, and you want to know how does the temperature change with respect to time? How quickly does the temperature move throughout the rest of the metal rod? So this equation says that the rate at which the temperature changes with respect to time is equal to a constant dependent on the material times the second derivative of T with respect to space, as in the distance from the heat source. Now, you might have a two-dimensional example of this in which heat is passing through a very thin two-dimensional plate, and two-dimensional plate because it's thin, and so we're not interested in the movement of the temperature with respect to the height of it. Okay, so in that case we would model the temperature changes in, say, a barbecue plate or a metal plate with a source of heat somewhere on it to be the same thing, but we have another y dimension. So partial T on T is equal to K times nabla squared T. Okay, or we could have a three-dimensional example in which the temperature is moving through a three-dimensional block of something. So that's very similar. And now another thing that we'll look at in week 12 is actually modeling the heat equation using a numerical method such that the rate at which the temperature is changing with respect to time is constant or zero. So that would be the steady state heat equation, where the temperature at each point remains constant within. Suppose it's insulated on all sides, for example, with perfect insulation. Okay, so in that case, you could have just the left-hand side being equal to 0, and so you would divide away the constant, and you would have just nabla squared T equals 0 in the steady state heat equation. Okay, so now let's have a look at some notation, because perhaps you haven't seen too much of partial derivative notation, although I'll remind you that we've already solved some partial differential equations of the simplest kind way back when we did exact ordinary differential equations in the earlier weeks of the course. Okay, but back to notation. So the second derivative of u with respect to x partially is denoted partial superscript 2 u partial x superscript 2. And that means the partial derivative of the partial derivative of u with respect to x. So remember, these are operators. You can treat them as operating on something. So the partial derivative with respect to x operates on the partial derivative of u with respect to x. And we can abbreviate this u subscript xx. All right. Similarly, if you see partial with a subscript of 2 of u partial x partial y, that means the partial derivative with respect to x of the partial derivative of u with respect to t. And so that we can abbreviate with our subscripts as ut bracket x to mean we're differentiating with respect to x partially the partial derivative of u with respect to t, but then we can abbreviate this even more and call it utx. Okay, but notice the t is to the left of the x, whereas over here it's the other way around. So there's a sort of swapping when you use this notation rather than this notation. Okay, so I'll remind you of Clairaut's theorem. Now this would have been covered in Math 201 briefly, but it's relevant here. So it says that if f and its first and second partial derivatives are defined and continuous, then the order in which you differentiate them doesn't matter. So f subscript xy is the same as f subscript yx. All right, so let's have a look at another PDE now, another famous PDE. The wave equation. This describes how waves move in a medium with respect to time. All right, so if u is the, say, amplitude of the wave, then the second partial derivative of u with respect to t is the square of the wave speed, c, times nabla squared of u. And so in one dimension, this is much simpler to look at. It just says that the second partial derivative of u with respect to t is c squared times the second partial derivative of u with respect to the one spatial dimension. And so this can be abbreviated as u subscript tt equals c squared u subscript xx. So this is a wave moving in, say, a metal rod. So if you look at this picture, and now you've got a wave. So, for example, this could be something like a slightly elastic rod where the amplitude is moving left or right. Okay, for example, a spring, I suppose, would be a fine example of this. The motion of a spring would obey the wave equation. So if you had a spring and you vibrated one end of it, so then you're asking how do the vibrations move through the spring. Okay, we've already talked about Laplace's equation, equation 36 here. So that is just the right-hand side of the heat equation where the left-hand side is 0. So this is the steady state heat equation, basically. So this is a time-independent partial differential equation. It arises in problems of steady-state heat transfer in a metal plate. So for example, a barbecue plate that's insulated on all sides so that no heat transfers through it, no heat leaves or enters the system. And that means that the temperature of every point within it stays the same over time. But those temperatures within it may not be equal to their adjacent temperatures. Okay. So we have the steady state heat equation with the rate at which T changes with respect to time is equal to 0. And so we get equation 36 there. All right, next we have Schrodinger's equation. So this is an equation that describes the strange behavior of subatomic particles. Remember, if you've done a little bit of physics, you learn that some very tiny subatomic particles have a duality in their behavior. In some descriptions, they behave like a wave, and in other descriptions, they behave like a particle. So the Schrodinger equation is relevant in that discussion. So it's a second order partial differential equation of this uppercase psi. And I think that's called the wave function. I don't know. I'm not a physicist, so I'm not an expert in that. All right, so it's used to find the allowed energy levels of a quantum mechanical system. It's the Schrodinger wave function. Okay, there we go. E is energy, V is potential energy, and X is position. Most PDEs do not have a simple algebraic solution, but rather numerical approximations to the exact solution. Okay, so, and to elaborate on that remark, it's just that it's really difficult to find an analytic solution in most situations, even though they may exist, but they may exist as strange looking infinite series. Okay, so there is some analytic solution. It's just that it's difficult to find, generally speaking, and even if you can find it, it's not so easy to represent it in a pretty way. All right, let's have a look at example 11.1. Let u of x comma t, now notice I've got the x and the t in the reverse order to what we had, I guess, up here. That's fine. Remember, we just need to be consistent about that order. Okay, let u of x and t be equal to sine of x and cos times cos of c of t. To show that u satisfies the wave equation, okay, then we need to differentiate. We need to take all of the partial derivatives. So the partial derivative of u with respect to t, remember we're treating x as if it's a constant, so we can pull that through the partial on partial t symbol. And then we're just differentiating cos of ct with respect to t. And remember, we need the chain rule for that, so that would bring out an extra c, but the derivative of cos is minus sine. So we get minus c sine of x sine of ct. Okay, now if we were to differentiate that again with respect to t partially, again we treat the sine of x as a constant and let that move through the differential operator. And so we're differentiating sine of ct with respect to t partially. Okay, we get c cos of ct for that, but now we've got to multiply that by minus c sine of x. And so we get minus c squared sine of x cos of ct. Okay, similarly, differentiating sine of x cos of ct with respect to x partially, we're now treating t as a constant, so that means we're treating cos of ct as a constant, and we're just differentiating sine of x. So the derivative of sine of x with respect to x is cos of x, so we get cos of x cos of ct. Now, differentiating that again partially with respect to x, the derivative of cos is minus sine, so our second partial derivative of u with respect to x is minus sine of x cos of ct. Okay, so now we'll pop this into the one-dimensional wave equation, and we see that u subscript tt is equal to minus c squared sine of x cos of ct. But if we just take the c squared out the front, we have c squared times bracket minus sine of x cos of ct, which is u subscript xx, as in the second partial derivative of u with respect to x. So it satisfies the wave equation, right, which was, remember, just this equation above equation 36 in one dimension. Now, so that's easy enough to solve analytically, but the difficulty in solving the wave equation is when you have more than one spatial dimension, right? So numerical approaches are very tricky to solve the wave equation, but sometimes that's your best option, is to have some very careful analysis of your wave equation numerically. And there are a couple different numerical approaches, at least, for solving such equations. The one I'm going to show you later is called finite differences, in which what we do is we write approximations of the derivatives, and then we write down a system of linear equations and solve that. Okay, so example 11.2. Let u of x and y be e to the minus x sine of y. Show that this u satisfies Laplace's equation. Okay, so the Laplace equation, remember, was nabla squared of u is 0. So what we do is we take our partial derivatives. We get uxx is e to the minus x sine of y, and uyy is minus e to the minus x sine of y. So if we add those two together, we get 0, right? They vanish. And so there is Laplace equation, u double x plus u double y equals 0. Okay, let's move on to our next section now that we've seen what PDEs are, how they get used, and how to show that some simple functions satisfy those. So now let's move on to solving PDEs just by integration. Okay, so it's like chapter 5, in which we were solving ODEs by writing down some PDEs and then solving them. So it's very much the same as that component of that chapter. Okay, so we solve simple PDE boundary value problems by integrating directly here. The integrals are taken partially, where we treat all other variables as constants. So we're going to have multiple letters, and when we have a plus c, again, like what we did in chapter 5, we have a function of the other letter in the place of the plus c. All right, so let's have a look at example 11.3. Solve the boundary value problem. U subscript x is equal to x, where we have u of 0, y is 3. So that's a boundary value. Here we're able to immediately integrate with respect to x. So we, on the left, we have partial derivative of u with respect to x. So that's separable. So we just integrate both sides with respect to x. Okay, now u subscript x is equal to x. So we just need the integral of x with respect to x partially, and that is a half x squared. Ordinarily it would be plus c, but here we have plus a function of y, because if we would differentiate a function of y with respect to x, we would get 0. Just like when we differentiate a constant, we get 0. So we have u of xy is a half x squared plus a function of y. Now we use our boundary value, u of 0 and y equals 3, to get more information on g. So we sub that into our function. So we've got a half 0 squared plus g of y is equal to 3, which was u of 0 and y. So that tells us that g of y is 3, and so we can write down that u of x and y is a half x squared plus 3, which solves the problem. Very simple. And usually they're not that simple. Okay, example 11.4. Solve the boundary value problem. U subscript xy is y squared, where we have the boundary values u subscript x of x and 0 is 7x, and u subscript 0 and y is equal to 4. Okay, so similarly we integrate u of x and y with respect to y, and we get u subscript x. So we just take the equation and apply integral with respect to y. What you get on the left when you do that is just the partial derivative of u with respect to x. Right? So that's what this is, and so that is the integral of u subscript xy with respect to y, but now we can sub in our PDE, the right-hand side of the PDE, and say that that's just y squared. So we're integrating partially y squared with respect to y. So that is a third y cubed plus some function of x. Okay, now we need to find what the function of x is, so we use our boundary values. So u subscript x of x and 0 is 7x, so if we sub in y is 0 here into u subscript x, we've got a third of 0 cubed, okay, plus our function of x. Now I can see a typo there. The f of x is up here, but now we've got a g of x. Oh well, sorry about that. It looks like I'm back to f of x is on this line, so that should say f of x there. Okay, so that tells us then that f of x is 7x. And so now we can sub that in, and so now we have an equation involving the partial derivative of u with respect to x, and we found out that it's 1/3 y cubed plus 7x. Okay, so next we've got to integrate this with respect to x, and then use our other boundary value to finish it off. Okay, so integrating that one with respect to x, partially, we've got 1/3 xy cubed plus 7/2x squared plus some function of y. And now we're calling that g. Okay, so now we're going to use our boundary value. U of 0 and y is 4, so we sub in x is 0 and y is y, and we're meant to get 4 out of that. So 4 is equal to 0 plus 0 plus g of y. So we see that g of y has to be equal to 4, and so we have our solution to that partial differential equation. Okay, so far we have only seen very simple PDEs to solve. Now I'm going to jump into a more complicated example, but very simple equation. So this is called D Alembert's solution to the wave equation. So before, remember, we showed that certain functions satisfied the wave equation. So let's go back. So this, for example, sine x plus cos of ct, we showed that this satisfied the wave equation, but now we want to take the wave equation and find general solutions, which is, you know, a much more difficult prospect than just showing that a particular function satisfies the wave equation, because there are many solutions. Okay, so next we'll look at solving the one-dimensional wave equation using D Alembert's solution, or means of characterizing the solution. Okay, so we're going to introduce two new letters, y and z. So we let y equal to x plus ct and z equal to x minus ct. By the chain rule, this is another version of the chain rule for partial derivatives. We have that the partial derivative of u with respect to t is the partial derivative of u with respect to y times the partial derivative of y with respect to t plus the partial derivative of a u with respect to z times the partial derivative of z with respect to t. Now, if you look at these and you think in terms of fractions, just in aid to memory of the rules, you see you would cancel the partial y's and the partial z's, and you would have a sum of 2 partial u on partial t. Right? So these are not fractions. It just helps you remember the rules, especially the chain rule and integration by substitution and so on. Okay, so that helps to get the right rule. Okay, so let's actually calculate these partial derivatives now. So looking at our expression there and differentiating this partially with respect to t, that means then that we're treating x as a constant. So the partial derivative of x with respect to t is 0. And the partial derivative of ct with respect to t is just c. So we can replace partial y on partial t with c. And similarly, differentiating z with respect to t partially gives us minus c. And now we can rearrange this expression, so factorizing out the c and using a differential operator, which is the difference of these partials, partial y and partial z, operating on u. So we've got the partial derivative of u with respect to t is c times this differential operator operating on u. Now similarly, we can do the same thing with partial u with respect to x. We use the chain rule, then we apply partial on partial x to each of y and z. Okay, so we get 1 in both cases, so this is just the sum of the two partial derivatives of u with respect to y and z respectively. And now we can put the u on the right hand side and display this as an operator. Okay, so it follows that the operators partial on partial t and partial on partial x can be represented as c times the difference of these two operators and the sum of the two operators. So that helps us to calculate the second partial derivatives in a similar way. So we find that the second partial derivative of u with respect to t is c squared times the sum of these three second order partial derivatives. And likewise, the second derivative of u with respect to x is the sum of these three second order partial derivatives. Now, the wave equation should be satisfied, right? So that's equation 37. So we can take these two expressions and substitute that into the wave equation. So partial u with respect to t, so the second order partial derivative of u with respect to t is this c squared times these three terms. So that we put on the left here. And that should be equal to c squared times the second partial derivative of u with respect to x. So that's what we have here on the right. Okay, now you can cancel the c squared, and you see that a lot of the terms will vanish. So the second order partial derivatives of u with respect to y and with respect to z, they're on both left and right sides, so they vanish. And so what we then have is we must have d2u on dy dz equal to 0. Now that's great because that tells us how to give a general expression for u. So we integrate this with respect to, let's see, which way does this go? With respect to y first, okay? And so when we do that, we get a function of z as our constant of integration. So we get just f of z there when we integrate partially with respect to y. Then we do it again. So we integrate and we get a function of y. So it turns out that u of x and t is a function of z plus a function of y. But remember, y is x plus ct and z is x minus ct. So our general solution is u is equal to f of x minus ct plus g of x plus ct. Okay, now we don't yet know what f and g are. Because remember, there are many possible solutions to the wave equations. Waves come in all kinds of shapes and sizes, right? And they satisfy the wave equation. So we could then have something that looks like sine of x cos of ct, or something else. So how do we get f and g? Okay, so these come from particular boundary values or initial values. So we want to interpret equation 39 as that there are two waves moving at speed c in opposite directions. But we don't know the shape of those waves yet until we specify boundary values. So let's have a look at that now. Okay, so let's suppose we have two functions, h of x and k of x, as our initial values. So that's when t is 0 here, but they could just be boundary values. It works nicely with initial values. So let's let h of x be u of x and y, and t is 0. And let's let the partial derivative of u with respect to t at x, and when t is 0, let's call that k of x. So now we want to write h of x as u, x, and 0, and then sub in what we have according to our last line. So that's f of x minus c times 0, because we're subbing in 0, and then plus g of x plus c times 0. Again, we're subbing in 0. So simplifying that, we see that it's f of x plus g of x. All right, similarly, k of x, we define this as u subscript t of x and when t is 0. Okay, so again, we want to sub in, well, in this case, we can just sub in that this is the difference. Now, this comes from, where was it? This last line. This comes from this last line on this page 104. Okay, so that's c times partial u on partial y minus partial u on partial z. Okay, so we take that form of u subscript t, and we sub in t is 0 into that. So what we have then is g subscript x for u subscript y, and u subscript z is f subscript x. Okay, so this is c times gx minus c fx. Okay, now we get that via the chain rule. So integrating and using these two expressions, so the top one comes from this, k of x equals c times that difference. And so we just integrate that line with respect to x. And then the second line is just f of x plus g of x is h of x. Okay, so we've written those in a way that we can see that we can just plain add them. So adding those two equations and then subtracting them will make the other term vanish. So in the first case, adding gives us 2c g of x is c times h of x plus the integral of k of x with respect to x. And then taking the difference, so second equation minus the first equation makes the g of x vanish. And we have 2c f of x is c times h of x minus the integral of k of x with respect to x. And so now we can divide both equations by 2c and obtain expressions for each of those functions. All right, so now that we've got expressions for each of those functions where h is u of x and t is 0, and k of x is the partial derivative of u with respect to t at t equals 0, we can write our general solution because we obtained earlier that u is the sum of f of x minus c times t plus g of x plus c of t. And so we can sub in these two expressions we have now, replacing the x by x minus ct, and the x and the y in, was that g of y? Yeah. So we can replace the y in g of y with, because now we know the general expression for g, we can replace that with x plus ct in here. Okay, and so that's these two expressions, and so we do some calculations and we find out that we have u is 1/2 the sum hx of x minus ct plus h of x plus ct, and then plus 1 on 2c times the definite integral of k between x minus ct and x plus ct. So that's what our general solution to the wave equation looks like. So we need those initial values. So now let's have a look at example 11.5. It's an example of this. So it says a wave of speed 3 meters per second travels through a spring with initial conditions. Okay, so this is our h of x and our k of x right here. So we're given these two functions. Calculate the wave function. Okay, we must solve the PDE u subscript tt is equal to 3 squared, which is 9, times uxx. Okay, so we've got these two things. This is our h, this is our k, just from these two. And then we just use the formula for our general solution and sub in, replacing the x here with x minus ct and replacing the k part of it with x plus ct, or just using this formula here. Okay, so we sub those in, we calculate our integral, and this is what we get. So you could go back and check that this satisfies that wave equation, and indeed it does. Alright, so that's a more complicated example. So this is D Alembert's solution of the wave equation, and then we saw an example of using that, which is significantly easier than generating the general solution. Now let's look at separation of variables, but for this part I would encourage you to go back into weeks 9 and 10, where Professor Margaret Marshman provided you with some videos and other resources on separation of variables for PDEs. Okay, so that I think you'll find very helpful. So I'll go over some of that here, but please go back and have a look at those videos. Okay, so assume the solution is a product of two functions of x and t respectively. Okay, so uppercase x of x and uppercase t of t. So taking derivatives with respect to x and with respect to t, we get these expressions here. First derivative of x with respect to lowercase x times t of lowercase t. This is our partial derivative of u with respect to x. And then differentiating that again with respect to x gives us the second derivative of uppercase x with respect to lowercase x times t of lowercase t. And similarly, the partial derivative of u with respect to t is uppercase x of lowercase x times the first derivative of t with respect to lowercase t. Alright, so we're going to use the familiar methods for separable ODEs. So let's have a look at the following example. A metal rod of length L has a fixed temperature 0 at each end. Okay, so we're going to use the heat equation here in one dimension. Initially, the temperature is dependent on the position. Okay, u of x when t is 0 is 6 sine of pi on Lx, where L, remember, is the length of the rod. We have the following boundary value problem. Okay, so the heat equation comes first, and then we have a condition at one end of the rod. So when x is 0, we've got 0, and we're told that here, fixed temperature 0 at each end. So that's how we write that boundary value. And then at the other end, which is when x is equal to the length of the rod L, we also have 0 for our temperature. And then we're told that initially we've got a temperature that depends on the position. So that's initially means when t is 0. Okay, so for that we can write this ux of 0. Well, that's already written there up in the problem. Okay, where k is positive. Assuming that u of x and t is a product of a function of x and a function of t, we take our partial derivatives just as we did on the previous page, and we sub those into this expression and simplify. Okay, so x of lowercase x, t dash of lowercase t is u subscript t, which is by the heat equation k u subscript xx, and then u subscript x, x was the second derivative of uppercase x with respect to lowercase x times the function t of lowercase t. Okay, so that's times k. All right, now this equation is separable here, so we can put the t's with the t's and the x's with the x's. Yeah, supposing this is a minus some constant. Okay, so which produces, so rearranging these, so just taking the t over to the right-hand side, we've got two simple equations without the other letter in them. So if c is 0, then we have x of lowercase x is c1x plus c2, and t of lowercase t is c3. So in this case, we have u is equal to c1 c3x plus c2 c3, but since our boundary condition says u of 0 at t is 0 and u of l at t is 0, we must have u of x and t is 0 in the case that c is 0. Okay, now separating the other case, if c is negative, then the general solution is, so that's to this second equation down here. Okay, so the general solution is from our work on second order ODEs. Remember, these are eigenvalues up there in the exponent. So x of lowercase x is c1 e to the power of the square root of c over k, and then times e, and then plus c2 times e to the minus the same thing. Okay, and so we get that u is this expression times some constant e to the minus ct. Okay, now since u of 0 and t is 0, which is u of l and t, we can sub in x is 0 and get some more information on this. So it tells us that u has to be equal to 0, so again we get that, that u is 0. Okay, now in our third case, if c is positive, then the general solution is, again from our work on second order ODEs, we have a cause and a sign involved. And then our general solution looks like this. Now the boundary conditions give us, once we sub in x is 0 into that, we get u of 0t is 0, so, and u of l and t is 0, so we must have c of 1, c subscript 1 is 0, and sine of the square root of c over k times l is equal to 0, or a is 0. So if a is 0, then we get u x sub x of, when t is 0, the boundary condition not satisfied. So we must have the other case, in other words, u is equal to c2 sine of the square root of c over kx times a e to the minus ct. Alrighty, so that gives us an analytic solution to the one-dimensional heat equation with these particular boundary conditions. Alright, so the other boundary condition, so now what we can do is get more specific on this so we can find our constants. Okay, so our other boundary condition, when t is 0, we have 6 sine of pi on L x. So that gives us that u of x when t is 0 is a c2 sine of the square root of c over kx is equal to 6 sine of pi over Lx. So that gives us a times c2 is 6, and pi over L plus some integer times pi is equal to the square root of c over k. So we now have u of x and t is 6 sine root 2 on x. From this, e to the minus ct. Okay, so if m is equal to 0, remember that's the integer multiples of pi, we have c equal to k times pi squared on L squared, and then we have our solution there. So we've also got the constant c. Okay, so that's all for this chapter. So next up, we're going to look at a little bit of physics in relation to the steady state heat equation. And so looking at approximations of these partial derivatives and using those approximations to write down some linear equations that we could then solve to find numerical solutions to some more complicated partial differential equations. All right, thanks.